Okay, well, we're very honored to have you with us today, Kathryn, Professor Kathryn Johnston. She's a professor in Columbia University at the Department of Astronomy. She received her PhD from the University of California, Santa Cruz in 1996. Her advisor was Professor Lars Hernquist, if I'm not mistaken. She's been also a member of the Institute for Advanced Study at Princeton University for 3 years before she became an assistant professor at the Wesleyan University, and then she joined the Columbia University in 2006, and she's been there since. She's currently the leader of the dynamics group at the Center for Computational Astrophysics, which is a part of the Flatiron Institute, which we have heard, I think, and chair of the Committee on Equity and Diversity in Columbia School of Arts and Sciences. Her research focuses on different aspects of the dynamics of galactic interactions generally and specifically for our own galaxy and M31, utilizing numerical simulations. Today's talk is entitled Snails Across Scales, or Fun with Phase Mixing. And what she's, I understand that from the abstract, it's that there are going to be results from the Gaia mission discussed, showing a detailed picture of our galaxy in 6 dimensions that reveal abundant signatures of departures from purely random samples drawn from equilibrium distributions. And the talk outlines some fun connections back to basic dynamical concepts and forward to interpretation and implications. So we are really looking forward to this talk. Professor Johnston, thank you very much for being with us today. The floor is yours.
Hey, thank you so much. And I've said this already, but just let me repeat in case you didn't hear, it's really delightful to get this invitation. I've never been to Athens professionally or personally. And pre-pandemic, I think this would never have happened. So this is one positive thing to be here. And also in particular from your university and the strong tradition in dynamics from your university, the roots there in galactic dynamics, and also great dynamicists coming out of Greece in general. So it's lovely to be here. Thanks for the invitation, the great introduction. As Despina said, I'm going to talk about snails across scales. This is actually a recent paper. I forgot to put this on the slide. The lead author is Saror Gandhi, if you want to look this up, but it's a continuing interest of me and a group of us continuing to look at this. Broadly, I would say upfront, this is a very focused one topic colloquium, and it's really to dive deeply into that one topic. I don't know about you, but we're all fairly tired of Zoom, so I try to keep it straightforward and also focused and not to jump around too much. And it won't be hours long either. But broadly, I want to talk about the vertical disequilibrium that has been observed in our galaxy, what we've seen and what it might be able to tell us. So this picture is a merging of our galaxy, the level at which it departs from equilibrium. Actually, the Gaia mission, let's take a step back, right? So Gaia is launched by the great Europeans, right? It's a gift to the planet from Europe. We're just coming to the highlights of Gaia, but even within a few years of its mission, it was giving us data for 2 billion stars across the galaxy. And if you think about it just for a second, Gaia has the accuracy to, if you put a tennis ball on the moon, Gaia has the angular resolution to see one side of the tennis ball versus the other side. And that actually, for us standing on the Earth, that actually means, in effect, because we can measure positions of stars in the sky extremely accurately, that gives us 2 things, right? It gives us distances incredibly accurately, and it all through parallaxes, and it also gives us proper motions perpendicular to our line of sight. The other way of looking at this if you can look at the difference between one side of a tennis ball to the other side on the moon, which is kind of like me just gently waving like this, you'd be able to see me waving on the moon. It's also equivalent to me going to Proxima Centauri and walking around Proxima Centauri, our next nearest star. So if I was glowing extremely brightly and going at walking pace, Gaia would be able to measure that as motion across the sky. The other thing is, so in other words, Gaia plus sky position and time is going to give us a full 6D motion if you include a radial velocity, a 6D position and velocity in our galaxy. So that's a phenomenal idea. We've gone from looking at galaxies in projection, including our own, to actually looking at our galaxy in 6 dimensions. And a lot of this talk will concentrate as we get further along to just within a local ball around the sun, but I'm going to start with trying to talk a little bigger picture first. Okay, so what are we going to do? We're going to dive into the Gaia data a little bit from some of the DR2 release papers that came out in 2018, so several years ago now. But just to give you the context of what I'm talking about when I say the galaxy is in disequilibrium. And then we're going to go back and just have fun with orbits. We're going to think about what orbits in the galaxy look like, and I'm going to remind you how those orbits project into different dimensions and what we might see. And we're going to remind ourselves of just one very simple, it's actually a kinematic concept really versus a dynamical concept, the concept of phase mixing. And we're going to talk about how we see the consequences of phase mixing throughout the galaxy in many different ways. And towards the end, we're going to get on to talking about origins of features we see and therefore predictions and interpretations. Okay, so for the context, Gaia goes out, measures positions and motions of the stars, and then it produces these beautiful maps. These are visualizations actually by Shervin-Laporte, but the data, they were originally made from Gaia data during the release paper in 2018. So you can see the scale here. The sun is sort of sitting at the center in the XY plane as it's projected at about 8 kpc. And you can see you're going plus or minus 4 kpc along this box. And each of these panels is color coded by the mean radial velocity, the mean vertical velocity, and the mean azimuthal velocity. So around in the disk or in and out in the disk or up and down from the disk. And I want you to just concentrate, we're going to concentrate in vertical motions in general. And the point here is, prior to Gaia, we had a few hints that the disk was not actually completely disk-like. We had hints, and this is prior to Gaia, the few years prior to Gaia, we were just starting to see hints that the midplane of the disk of our galaxy is not one plane. It actually wobbles up and down. And what you're seeing here in the Gaia data, just look at this amazing resolution. We're talking about minus 4 kilometers per second to 4 kilometers per second. Being able to measure our speeds that accurately in this dimension, we're able to see some of this wobble. This part of the local area around us is just outside of the sun, away from the galactic center, is going up, and inside is going down ever so slightly. So the disk is wobbling up and down, and these are on small scales. It's not the whole of the disk wobbling up on down on one side versus the other side, which would be a classic warp. This is locally. There are ripples in our galactic disk. And you can ask, well, why would that be? One obvious culprit is a satellite galaxy impinging on the parent galaxy. So I've actually, this is a fun video for me. It was, it's a visualization made by one of our undergraduates who clearly has some Greek heritage here. Actually, his parents are immigrants from Greece, Anastasios, Andy Tsanidakis. Let's see if I can play that again. I'm going to go back and play it again. And the simulation is by Shervin-Laporte, who was a postdoc with me at the time. I've spent my career sort of really thinking about satellite galaxies and how they're disrupted by the parent. But you can really see how this satellite slams into the disk of our galaxy and really makes differences here. And especially on that second passage, you can see, I'm going to do it one more time. you can see the beautiful wobble in the disk. So watch it come around for first passage, and on the second passage, you can literally see the ripples spreading out through the disk. And of course, we do have satellites. There's evidence for satellites historically. This one is supposed to be on an orbit similar to a satellite, current satellite, the Sagittarius dwarf galaxy. We're going to come back to that satellite towards the end. And this is a model where that satellite has quite a large mass, so it affects the disk a lot, but it allows us to see the sort of effect you expect to see. Okay, great. So if we just look at a few snapshots here to get more of an idea from the same simulation. Early on, this is in density. You can see the disk is calm and featureless. And this is in vertical velocity, going up and down by quite a lot more than the Gaia data. But again, it's calm and featureless. This is a snapshot where you can see, actually, it's just the Sagittarius is going through the disk. And you can literally see the local disturbance in the vertical velocity. Sagittarius is going through the disk. And you can see significant up and down motions here of order tens of kilometers per second, because as I said, Sagittarius is pretty massive in this particular simulation. And then towards the end of the simulation, you can see that the coherent structures have wound up or phase mixed into a more messy structures over time. But the fun thing here is we can compare these simulations that were actually run pre-Gaia. They were run before we had Gaia DR2. We can compare some of the results between the simulations and the data. So in the top panels, you're seeing the data that I just visualized from Gaia. And in the lower panels, the white outlines the size of the top panels and location. And in the lower panels, you're seeing the simulations color-coded the same way. So if we just look at the VZ panel, in the simulations, you can see there's up and down motion on similar scales across the galactic disk as seen in the observations. The amplitude is bigger in the simulations, but the scales of the ripples are very similar in the simulations. And that's seen not only in VZ, but also in VR and V5. And to say this one more time, these simulations weren't run to match the Gaia data. They were run to match what we knew about the interaction of Sagittarius with the galactic disk. And so I think it's really fun that they actually match reasonably closely. But what you're supposed to be taking away from this in terms of context is this picture of our galaxy. We've always thought of it as a relatively quiet backwater of the universe, and I think that's still true. But what we're saying now is even in this quiet backwater of the universe, the galaxy is fluctuating and being impinged on at an order maybe 10% level. And what does this mean? Well, it means it's fun for a start to think about interactions. But the second thing I would say is that it has implications for how we model and interpret our data. And what this means is if we want to do better than of order 10% interpretation of our data, if we want to map our Milky Way's dark matter halo, that's a big question. If we want to map that as a function of radius and in 3 dimensions, and our galaxy is the one place we should be able to do that, we need to come up with better ways of modeling the data. The classic equilibrium models of the galaxy are insufficient for us to really take advantage of the detail that we could learn about our galaxy that Gaia offers. We really need to start thinking about modeling systems that are slightly out of equilibrium, systems that are not fully phase mixed, and we'll get to what I mean by that in a minute, and systems that are non-random as well to take full advantage of the data. And that's really the theme of the talk. Okay, so Maria told me that you don't usually have questions during the talk, but if you do, I cannot see you. Please feel free to unmute and jump up and ask a question at this point. Otherwise, I'm going to go on. Okay, so for the rest of the talk, really all we're going to talk about are orbits in the galactic disk. So let's just go back and remind us what orbits in the galactic disks looks like. And I'm taking a lovely illustration from Wilma Trick's PhD thesis to illustrate this. Most basically, in this XY plane that the Gaia data introduced us to, so the XY plane, the sun would be about, in Gaia coordinates, it was -8 kpc. So in the XY plane, that's the galactic disk plane. Largely the disk orbits are moving on very nearly circular orbits with a speed of 200 kilometers per second. So broadly, orbits go round and round in the galaxy. But if you zoom in here, you can see that Wilma's actually illustrated 3 different orbits here. One, which is almost, the red one, almost exactly circular. The blue one is not quite circular. It's going round and round in the galaxy, but also oscillating backwards and forwards in radius at the same time to form something of a rosette. And the green one is slightly more eccentric than that. So now we're going to look at this in not just position and not just velocity, but look at position and velocity at once. And to do this, we're going to, let me introduce here what's actually happening in these 2 dimensions at once. So the classic way of thinking about this is to think in terms of epicycles, right? So the red orbit exactly follows this black curve in the X-ray plane, and it goes in a circular orbit. The blue orbit is following the black curve, the center, the black curve, but then it's making a little oscillation in R around a central guiding radius. So the central guiding radius to the blue circle that's moving along the black orbit. And then the epicycle is going around that. And that in effect means that if you put this together, you form a beautiful rosette. And if you have a more eccentric orbit, then your epicycle is bigger. Now, this is what I was trying to say before. If we plot that in terms of both position and velocity now, and if we plot what is the radius of the blue orbit compared to its radial velocity, so its radial velocity oscillates up and down. When it's at apocenter, so this point, no, sorry, I'm doing this wrong. When it's at apocenter, furthest from the galactic center, its radial velocity is 0. When it's at pericenter, closest to the galactic center, its radial velocity is 0 by definition. When it has a positive velocity, then it is increasing in radius. And when it has a negative velocity, it is decreasing in radius. Sorry, I went ahead a bit fast there. So let me just do that one more time. So in other words, this radial motion projects into the RVR plane as a little circle. And because the red orbit or orange orbit is not going in and out, it just projects as a dot here. And the green orbit is going in and out and up and down, in and out more. So it projects as a larger circle. And we're going to be thinking a lot about this plane in terms of understanding projections in the galaxy. Actually, more specifically, we're actually going to be thinking about the same thing, but now we're looking at the ZVZ plane. So the orbits are going round and round. They're going gently in and out as they go round and round. I can't actually do that, demonstrate that very well. But they can also be bobbing up and down. The 3 that Wilma has chosen, the green one is actually exactly planar. It's not going up and down at all. The blue one is going in and out and up and down. And the red one is going up and down, but not in and out. So if we project these to the ZVZ plane in the same way we did for the RVR plane, then the red orbit is producing a small circle in the ZVZ plane here, and it's going in this direction, and the blue orbit is producing a larger circle. Okay, so this is what orbits are doing, and this is how we can dissect them in all dimensions, in 6 dimensions, by making projections of our data in different ways. And the bottom line here is the stars are going round and round, and they're going up and down and in and out in the galactic disk simultaneously and all at once. And another connection to make here is to remind ourselves that what this means is you can also label each orbit by a phase along the orbit, right? So apocenter and pericenter, or maximum Z height and minimum Z height, are different phases of the Z oscillation. So we can actually also label this with an angle. And in a way, what we're seeing here is a simple projection. What we're seeing is a cross-section of orbital tori. If people are familiar with action angles, we're seeing cross-section of orbital tori, where each of these loops is a constant action, and the angle around the circle roughly projects to an angle, a physical angle in action angle coordinates. But you don't need to know that, have delved into actions and angles to understand the rest of the talk. You can just think in this plane and the angles in this plane. And the last thing to show before I go on is just to give us a sense of timescales here. These are orbital timescales. The longest orbital timescale is the azimuthal timescale in green. So of order, at the sun, of order 250 mega years, but further out of order 400 mega years. So get used to those numbers. The azimuthal timescales are hundreds of mega years, and the radial and the vertical timescales are a similar order, but slightly less, of order 2/3 or even a half of that in terms of the vertical and radial oscillation. Okay, so that's orbits. Now we're going to go from orbits to think about phase mixing. And the easiest example to show what phase mixing means is to think about pendula. But actually, before I get there, I want to give some credit here to my collaborators, Adrian, Jason, Saror Gandhi, who's the first author on the paper that we've published so far, Shervin Laporte, who did the simulations, and David Hogg. Okay, so I just wanted to put some names and faces to the other collaborators here. Let's now go on and talk about phase mixing to remind ourselves. So let's think about phase mixing in a different context. Let's think about pendula. If you have a set of pendula, and say they start at 0 angle, which will be the vertical, and they all start at the same phase, but suppose they have different periods, which is what we just showed 2 slides ago. At different radii in the galactic disk, you can have different periods, and also for different amplitudes of oscillation vertically, there can be different periods to our orbits. So these are orbits of pendula. They all have different periods, but say they start at the same angle, and you give them a nudge, so they fly up. A quarter of a period later, they're almost still at the same angle. Half a period later, they've come back down, and now you can see there's a small range in angle. And if you go back up and back down again, you see a larger range in angle. So the angle is also the phase, right? So this is what phase mixing is. You start with pendula all at the same phase, but over time, those phases get mixed up. And if we make that as a plot of phi versus v phi, and you say that these objects all start at the same angle, lined up, this is the black line, and they're moving in this plane in the same direction, they're going to maximum angle to minimum angle, maximum to minimum. Then what you would see over time, if they have different time periods, is that the ones that have the shortest time period, so after a while, the ones with the shortest time period are slightly ahead in phase than the ones with the longest time period. And as time goes on, the degree to the ones with the shortest time period are ahead in angle, in phase, than the ones with the longest time period increases. And you end up with a spiral pattern in this angle versus v phi phase velocity plot. And that is phase mixing. Okay. Any questions here? I'm going to carry on. Right. So now let's go back to the disk and talk about phase mixing in the galactic disk. The same thing can occur in the galactic disk. Here's our now ZVZ instead of phi v phi plane. This is the ZVZ plane of our phase space projection just in the vertical direction of our galactic disk. And if you remember, there are orbits that are going around in this. The orbital paths are circles in this, and these represent stars gently going up and down in the disk, either a little bit or a lot. And the thing to remember also is that the orbital time scale for the star to bob up just a little up and down is smaller for the orange star. For the blue star, it's longer because it's going further up and down. Now we're going to zoom in on the Gaia data. We're not looking at a significant fraction of the galaxy. We're looking at a small fraction of the galaxy. We're going to look at a sample of about 7 million stars in this region where we have full phase space information. And there was a classic plot of those stars made by Teresa Antoja on the day after Gaia DR2 came out. And she made a plot of those 7 million stars in this plane. And this is what she saw. So what you can see here is a spiral pattern. So I've set you up to think about phase mixing. But actually, let's step back for a second. I forgot to say this. Let's go back. Pretend I didn't show you that. Try and imagine what you think we were expecting to see in this plane. And then we'll go on to look at the spiral. And actually, I'm going to stop for a second. I see something in the chat. I just want to check. Ah, right. It's just for Maria. So that's fine. So I can see the chat. If people want to try and put questions there, I might not catch them, but just a thought.
Yes, I will keep my mind.
Yeah.
Okay, I will keep in mind.
Okay. Okay. Good. So here are the orbital paths. If the galaxy was in perfect equilibrium, what would we expect? If the galaxy didn't have ripples in it, right? It would be, that would mean it was the same amount of stars above and below the disk. And if that's going to maintain, then you need the same amount of stars going up as going down. Otherwise, that if there were more stars going up, then the whole disk would move up, right? So in other words, if you look to this plane pre-Gaia, what we imagined we might see would be balls in this plane. Like if you did density, you would see contours that were isodensity contours that were basically circles in this plane. And if you made the plot that Antoja shows here, what am I doing? there we go. Where she plots, she's not plotting density, but she's plotting the mean V phi as across this plane. Pre-Gaia, we would have expected this to also just show density contours. In other words, yeah, you would expect not density contours. You'd show mean V phi contours that would be circles, but we don't see that, right? We see a snail, and that's fascinating and exciting. And as Teresa pointed out in the first place, this is a signature of phase mixing. And what that tells you actually is that something must have happened in the past to align things in phase. And that thing in the past that aligned things in phase and made phases non-random, what you're seeing is a signature of that past alignment phase mixing away. And of course, there's been many papers. I haven't updated this for a few months, but these are some of the papers written about this. And this is what we're going to delve into in the last part of the talk. Now, going back to the simulations for a moment, we, of course, were sitting, actually, the morning this came out, Shervin and I were sitting in the Center for Computational Astrophysics, looking at this plot. And we had Shervin simulations in hand already, as I told you, run pre-Gaia DR2. And so it was a pretty simple matter for Shervin to, on the very morning that this paper came out, make a plot of what we see in the simulations. So he zoomed in on a local region sometime after the interaction with Sagittarius in his simulation. And this was the global view. Now he zoomed in on a local view and made a plot the same way Teresa did of Z versus VZ, color-coded by V phi, and you could see a spiral. And this was tremendous fun to again see something in the simulations. It's obvious it should be there in retrospect. In fact, if we'd been really smart, we would have predicted this, right? But no. But it's really fun to see it in the real universe and then see it in your simulated data. And moreover, notice that the resolution in this data, the simulated data, is far from matching the resolution that we have in real data now. And that's actually another challenge for galactic astronomers. Okay, and on that note, I have to show you a really crazy simulation, or really crazy visualization of a simulation that Jason Hunt has run since then. Because we've realized that, of course, to study these things, we need much higher resolution simulations. So the simulation that Shervin ran had of order, I think, tens of millions particles in the disk. And Jason's simulations have hundreds of millions. So what you're supposed to see here, right, let me stop that for a second. I'm going to go back and we'll start it again in a minute. What you see here is a visualization by Jason Hunt of his simulation. You're looking down on the galactic disk, but now each little blob here is a little ZVZ plane. You're plotting the ZVZ plane for each little region of this disk. And I'm going to play it now. And you should kind of, it's pretty psychedelic. And it looks quiet at first, and then as the interaction with satellite Sagittarius comes along, you see snails or rather spirals appearing. And the fun thing is, it's just repeating over time. You see these spirals locally in each of these boxes in the ZVZ planes. But the correlations between the boxes, the fact that these boxes, these are not random spirals in the boxes. They've been set off. So this is a still, just to try and make the point. These are not random spirals as you go across the disk. They're different signatures of interactions. And presumably the local ones, these are coming from the same interaction, but they've ended up at different parts of the disk. So let's go back here. The fact that they're coming from similar interactions and then spreading over the disk over time means that you see spirals forming locally, but you also see spirals in the correlations in those patterns globally. And this is what I mean by snails across scales. You're seeing spirals locally and globally. There is an immense amount of information waiting to be exploited in this very simple physics of phase mixing across our galaxy, which is tremendous fun. Okay, so let me just talk about a little bit more about that to talk about the phase mixing, because I talked about spirals locally and globally. And to see that in general, let's go back and ask, where did those stars from that Gaia come from, that Gaia is looking at? So let's take a ball of stars, and this is just conceptually. This is the XY plane now, so we're back just looking down on the disk. Here's a ball of stars today. Where were those stars in the past? Well, let's take a star here. Maybe that star is actually on in this local volume, but it's actually on an epicyclic orbit that is going around the galaxy, and its guiding center is slightly within the solar neighborhood, a smaller radius. Well, in the past, say here was the sun sometime in the past, the solar or the circular orbit sometime in the past. At that time in the past, that red star would have been lagging, would have been further behind than where the sun is, because at that time in the past, it's gone a further angular distance. It can travel a further angular distance. The red star can travel a further angular distance than the orange star in the same amount of time, because it has a shorter orbital time period. So we can do the same thing with a blue star that today happens to be in the same volume as the sun. And you can actually find that that star also would have been in a very different volume, and actually even more different than the red star. So the point is, these stars that we see locally today actually come from all over the galactic disk. And so and this is another form of phase mixing. It's actually your phase mixing as you trace back in time, the stars that are today at one phase spread out over time. And that's another form of phase mixing that we're going to be able to use to our advantage. So now that we understand that we've got this local sample, that we're seeing stars, the signature of stars oscillating up and down at different rates, but also those stars come from different parts of the disk, let's talk about mechanism and talk about what's actually happening. So let's make a toy model now. Here's the galactic disk. There are those three stars at some point in the past in the disk, as we just saw in the previous view graph. The red slightly behind the yellow, which is slightly behind the blue. And here's Sagittarius coming through. And what you can notice is that for the yellow star, as Sagittarius comes through, as it comes through from the top, in terms of just the vertical acceleration, as it comes through from the top, the yellow star is going to be pulled up. And as it goes down, the yellow star is going to be pulled down. For the red star, as Sagittarius is coming from the top, the red star is furthest away from Sagittarius. It's closest at the disk crossing. And when Sagittarius goes a bit further, it's going to get closer along its orbit to Sagittarius. So its acceleration is lowest as Sagittarius is coming down and higher as it leaves. And the blue one is backwards. I can show you this in a plot. This is what I'm trying to say in my bad sketch. The acceleration on the yellow star peaks beforehand, goes through zero, and then goes through a negative peak afterwards. For the red star, there is a positive and a negative peak, but the negative peak outweighs the positive peak, and the blue star, it's opposite. So if we color code the disk now by the net acceleration, so this is not integrated overall, but we color code the disk with Sagittarius passing through here. What is the net acceleration if we just add up the acceleration over time due to that disk passage? The point here is that from one disk passage, different parts of the disk see different accelerations. So what's plotted here are stars on different radii at different azimuths in the disk. And this is showing you the velocity this should be acceleration. The acceleration that those stars are feeling over time due to the disk passage of Sagittarius. And the key point here is that these stars are all experience that disk passage in different ways. So if we put this together, phase mixing plus mechanism. Phase mixing tells us that stars that are in the local volume were in different parts of the disk in the past. And the mechanism is telling us that stars that end up in the local volume or different parts of the disk in the past experience interactions with a satellite differently. So what this is telling you actually, this is telling you that in this phase spiral, this is Antoja's phase spiral, and we've just projected it in a different way, and it's now color-coded by density. But this is the local real data from Gaia. This is telling you that this local data contains stars from all over the disk that have experienced interactions in different ways. In fact, we can calculate for this local volume. The orange is the location of the stars, so number of stars as a function of radius. This is the location of the stars that we're observing in that volume. And what you're seeing in blue are the guiding radii of those stars. So it's telling you that these stars have very different mean orbital radii. So one thing that's really fun to do is to take this local volume and ask, okay, let's look at all these sets of stars separately. Let's split them by their guiding radii, not the current radius, but their mean radius as they orbit. And let's order them by that and ask what we see. So in other words, this is the full data set. We can split it into stars whose guiding radii are smaller than the sun and stars whose guiding radii are larger than the sun. And what you should be able to see here is that you get different spirals, slightly different spirals in every case. And this is a combination of two effects. One is that the winding is going to be slower further out in the disk. Stars that mainly spend their time further out in the disk, the winding is going to be slower. But it's also true that these stars experience history in a different way than these stars. Ha ha ha. Now I'm going to show you the same thing, but I'm going to show you it as a movie. So this is taking the Gaia data and splitting it in those radial bins. We're going from the outside to the inside as this number, the angular momentum, goes down. And then I think we reverse and go back up. So it goes down to the smallest radii possible, lowest angular momentum. And this visualization was made by Sherman-Laporte. And then it's gone to the bottom, the lowest angular momentum. Now it's going back up. And we're going back up and back out through the disk. And you can really see that the spiral patterns change. And the wonderful thing about Gaia is, okay, this is fabulous. We've only looked at one small patch of the disk. Future Gaia data sets will be able to do this for many patches. So it's really, even though phase mixing is one of the most simple concepts in kinematics, it's not even dynamics, there's immense amount of information here. And this is just showing you on the same thing that we were now able to do with our higher resolution simulation. This is simulated data and showing you how different groups in the same volume in simulated data in different guiding radii groups show different spirals. Okay, excellent. So I'm going to skip the next slide. I want to go on and actually, I'm looking at the time. I want to go on. This is essentially saying the same things that I just talked about, saying that the different spirals arise from different histories in the disk. I want to end by actually moving away from the snail for a little bit to talk about something that was we found in the course of our understanding the snail, which is to talk a little bit about the current interaction of Sagittarius with the galactic disk. Okay, so what I wanted you to get from the snails part is this idea that even looking at a local volume of stars, you're getting signatures of history spread throughout the disk. So I'm not giving you interpretations yet. What I'm giving you is potential of the amount of information that we have, even in one local volume. And then Gaia DR3 is coming up soon, and then there'll be later data sets. We'll be able to do this not just in a KPC volume around the sun, but across half the galactic disk by the end of Gaia. And I think that is going to tell us an awful lot about interpretations of what's happened. So that's snails across scales. The last part, the very last part of the talk, is a little bit of an aside, because if we go back here and we look at the simulation of Sagittarius, we can go back to where we started from, and we can go back to the global view and go to the global snail now, get away from the microscopic snail to the macroscopic snail, and ask about these ripples. The fun thing about the interaction with Sagittarius is that it's still ongoing. So here's Sagittarius in its current position and current motion. This is from Vasiliev et al. Here's the galactic disk and the sun to give you a sense of scale here. Sagittarius is about twice as far from the galactic center as the sun. We have to look almost directly through the center to see Sagittarius. We can also see, but this is simulated data, not real, but it closely matches the real data. We can also see beautiful streams from Sagittarius as it's being pulled apart by a galactic disk. So our galactic disk is also attacking Sagittarius in the same way that Sagittarius is attacking the disk. The key thing here, that point here, is Sagittarius is about to go through the galactic disk. And so for a long time, we've thought of it as about to have its interaction with the galactic disk. If you look, if we redo some of our calculations that we made about accelerations, net accelerations, and effect on the disk, and we ask what those look like for stars in different locations around the disk, just as we did before, and we plot the acceleration as a function of time that we expect due to Sagittarius. The orange is the future disk crossing, right? And Sagittarius has not yet crossed the galactic disk. So actually the current time is not marked here. It's actually at 0. So it's here. That's the current time. The orange is the future disk crossing. And the point of this plot is to show that at almost every radii, except for perhaps the outside, the bulk of the interaction that these stars are experiencing has already happened. And this is because, let's go back a minute, Sagittarius along this orbit is not going directly vertically through the disk. It's actually sweeping under the disk and then going out. So for most of the stars across our galactic disk, the future disk crossing, the impact of Sagittarius, has already happened. So this was really fun when we realized this, and it caused us to go back and ask, well, okay, what do we think that would look like? And this is a simple toy model description of what we think this would look like, meaning a test particle model, not fully self-consistent and only of the current passage. And the blue patch is where in this model, Sagittarius is just sitting below the galaxy, still pulling this blue patch down. The red patch are stars that were interacting with Sagittarius as it was coming under the galactic disk. It takes 100 to 200 mega years to do that. So that means these stars experienced that passage. They were over here, they experienced the passage of Sagittarius going under, and they've actually gone from being just oscillating with no mean vertical motion, they're actually coherently moving up in reaction to the passage of Sagittarius that has already happened. And this was a test particle model of a single passage as Sagittarius comes out of the disk. This is the results from the fully self-consistent simulation. And they don't look exactly the same. They have many different passages in them, the fully self-consistent one. But I draw your attention to the blue patch here. In the fully self-consistent case, Sagittarius isn't in quite the same case. And note that there is a blue patch here and there's a red swirl here. And we think that those signatures are robust. We think these are signatures of the current passage of Sagittarius. And it might be something we could see. In terms of the microscopic scales, if we go back to the ZVZ plane, there are no snails within these regions yet. It's too early. What you can see is the mean offset down below the plane, and the mean offset, this is less obvious, up a little bit in this case. But there are no snails here. So really, we're interested in the global interaction. So if I plop down a circle here, just to emphasize this, here's a circle, just to guide the eye a little bit, to show you, I'm next going to show you some data. Here's data from Gaia. So Sagittarius is on the opposite side of the galaxy. Here's the Gaia data, where we're looking at the mean Z and VZ, the mean VZ in the Gaia data between -10 and +10 kilometers per second. Here's the sun, here's the center of the galaxy. And it's tantalizing that you can see this positive ring. Let's go backwards again. You can see a positive ring around the same part here. Of course, we cannot see to this side of the galactic disk yet, because the most prominent signature is where Sagittarius is sitting below the disk. So this is really fun. It's something to look out for in the future. Again, the scale of the Sagittarius in the simulations is probably too high. So if you notice, this Z-axis is scaled by 10 to the 10 solar masses over the mass of Sagittarius. And if Sagittarius was 10 to the 10 solar masses, we would expect oscillations of this scale. But we think the Sagittarius is only of order 10 to the 9, so the oscillations are going to be very tiny. But nevertheless, it could be a fun thing to try and find this global pattern. Let me go back for a second. To try and find this global pattern of the inner galaxy across the galactic disk as a signature of the ongoing interaction of Sagittarius. Okay, so that's just about everything I wanted to say. I wanted to talk to you about snails across scales. And I don't have results as in this is what is happening to our galaxy. This is really an advertisement to say there's a lot of information in the Gaia data that's far from exploited, that we're missing the right tools to exploit that data. I mean, this rewinding the snail sounds like an easy proposition, but I don't think anybody's done it correctly yet. But it's completely worth the extra effort to understand how to build disequilibrium, non-random and unphased mixed populations, and how to interpret them in order to understand the past and also the future history of the Milky Way. So that's it. Thanks very much. And I will stop sharing, so hopefully I can see, and I'll start presenting as well. So hopefully I can see some of you again. And
Yes.
Maria, do you want to call on people for questions, or shall
Yes, yes, I will do that. Thanks very much for this excellent and very descriptive talk, even for non-experts. So at least we were able to understand the basics, hopefully. So I see already one hand raised by Despina. So please go ahead, and I would like to encourage everybody to ask questions. So we have plenty of time.
Thank you for a very, very interesting talk. Thank you very much for that. I wanted to ask you the following. When you showed us the spirals, the small scale spirals in the big picture with the other spirals sort of showing as well, and the correlations between the different spirals at the different scales, what is the what determines the scales?
Yeah, good. I'm gonna just share that screen again. But hopefully I'll be able to, I can still see.
That one. Mm-hmm.
Yeah, so everybody can see that, right? I'm not gonna go presentation mode because then I can still see you. Right, so I think there's two different things going on here, right? So it's all about clocks, right? Dynamics is all about clocks. So you have the clocks going up and down, and you have the clocks going round and round, right? The rate of the winding up or the phase mixing is determined by the parent galaxy clocks. The Milky Way's clocks, how fast are you going to wind up these spirals, is determined by the parent galaxy clocks. Of course, the size of the initial offset is determined by the mass of the object, the mass of Sagittarius, and the number of interactions is determined by the orbit. So that's the Sagittarius orbits. But if we forget the multiple interactions, for a single interaction, the size of the offset will be determined obviously by the velocity, but mainly say for the same velocity, the mass of the object. And then the scales across the disk, how much they ripple across the disk, that's all to do with the parent galaxy. So the reason why these scales are interesting really is that they also, and I didn't say this, so thank you for setting me up to say this, they're telling us about the parent galaxy, not just about history. The degree of the winding tells us about history, but the scales that you're pointing out, like how big is the ripple going up and down, and what is the shape, actually the shape of the snail, you can see that it's got some corners to it. These are all telling us about potential of the galaxy. So you learn a lot about the parent galaxy as well as the satellite. And that's a great question.
Thank you. That's very interesting. Yeah, thank you. And also, can I ask just a very quick question as well? I suppose, do you expect something similar, maybe on a smaller scale at this stage, from the interaction with the Magellanic Clouds?
Yeah, great. Sherman has also looked at this in an earlier paper, and what we're expecting to see is that the Magellanic Clouds, if we compare Sagittarius and the Magellanic Clouds, we expect that the Magellanic Clouds influence may be more apparent in the outer galaxy. And that's, it's more massive than Sagittarius, but it's also more distant, and it's interacted for less long. So the exciting thing there is that a lot of the Magellanic Clouds influence, we think, is transmitted via the dark matter halo. There's the direct influence, but there's also the distortion of the dark matter halo. So the prospect there is, once we can do this in the outer disk, we might find a quite different nature to the spiral, and that could be either a signature of directly the Magellanic Clouds or the distortion of the dark matter halo. So yeah.
Because in the same sense as you described, you expect the potential to be depicted in a sense in the scales, right? So
yes.
Okay, this is
fascinating. Yes, but the thing to remember is the LMC is just creating the perturbation. The scales and the disk are all about the disk itself and how it's responding. Right? Yeah.
Great, thank you very much. I think we have a lot of very interesting things coming.
Yeah.
So I see also one more hand raised by Panos Patsis. So if you would like to unmute yourself.
Yes, can you hear me now?
Yes.
Great. Thank you very much for the very nice talk. My question is the following. Can we somehow, does the information of the underlying dynamics, I mean the initial dynamics before the interaction, survive in the data? Can we have an idea, or can we retrieve it? Can we have an idea where have been initially with respect to resonances on the disk of the bar of the nearby spirals or something?
Right. No, you raise a good point. So a lot of this will be challenged by what you're bringing up. Of course, there are dynamical interactions going on with the bar and the spiral arms as well. The hope is we'll be able to do both, in the sense, although it's not completely clear, in the sense that the bar and the spiral arms, the main interaction is in the radial and in-plane motions. And Sagittarius is on such an orbit that the main interaction is the up and down motion. So I'm hopeful that we will be able to do both. And there are, I'm sure you know, there are Gaia papers where you look at the local neighborhood and you look at the in-plane motions, and there are things that people are interpreting as resonances with the bar. That actually, that's Wilma Trick's work. That came out from Gaia DR2. The early papers, she was the one who led those.
Sure.
So I'm hoping we'll be able to do both. Does that help?
Yeah, well, and of course we have also vertical resonances. Although we are far away from the end of the bar, there must be a higher order resonance even there. So up and downs are even taking place there.
So actually, yes, no, very good point. I love that. Let's go back here. So there's one, and I'm going to, just to get the name right, we're going to go back and look here. Right, this paper by Kolpaskov is it exactly what you're talking about? How the buckling of the bar might itself set off some snails. So the beauty here is, this is why we want to go here. We want to go to this global view, because you can imagine a bar buckling. It's got two ends, which would be maybe in sync. I don't know, maybe you know more about bar buckling. I don't mean bar buckling. I mean bar formation, the buckling of the disc to form the bar. Yeah. Right? Then you can imagine that you would get sets of snails set off symmetrically across the disc, and you'd see a global pattern to them, which would be like a quadrupole pattern. Whereas Sagittarius going through this, you would expect globally it would be a dipole pattern. So the hope is that we'll be able to do everything. I'm not ready to promise because there's a lot going on, right? But I think the point here is this is very simple physics. So the hope is that we can, even though it sounds that things got more complicated because the galaxy is in disequilibrium. I think the trick is to find, not to try and model the whole galaxy, to model the little things that are being thrown around and are out of phase, or are being put into one phase and are phase mixing, rather than trying to build a full model of the equilibrium and the disequilibrium. We just model the reactions to the disequilibrium. Is that making sense?
Of course, yeah. Okay. Well, there are things that can be done there. Of course, yeah. Sure. Thank you. Yeah.
Yeah.
So, are there any questions from the younger audience? Till you think one, I mean, I'm going to ask a very simple question. I didn't quite understand how, I mean, you mentioned that the amplitude of this mean VZ velocity in your simulations, the last one, is at least one order of magnitude smaller than what is measured. And I was wondering, what would you need to change in your simulations to kind of obtain the observed value? Because as you described it, it looks like that the physics are rather simple. So I'm wondering where this difference might come from.
No, it's super. I think maybe I said it backwards, but I just want to repeat it the right way. The amplitude in the simulations is higher than in the observations. And the simplest interpretation of that is that the mass of Sagittarius in the simulations is too high. So conceptually, this actually goes back somewhat to Despina's question. Conceptually, suppose you have, if you could run a simulation with two different mass satellites, but on the exact same orbit, then all the timescales, and in the exact same galaxy, all the timescales, all the interaction timescales, everything's the same. The only thing that's different is the size of the tug and the acceleration. So that basically means that everything should be the same so long as you're in a linear regime. So probably no more than a few % of the mass of the parent. Everything should be the same other than the amplitude. So our best guess as to why the amplitudes are off, because the scales of the interaction, as in spatial scales, work quite well. It's just the velocity amplitude. Our best guess is actually we've got the orbit reasonably well, and the model of the Milky Way is reasonably good, and the mass is off.
Okay, so it was not like a numerical reason that you had to increase to use a larger mass for the satellite galaxy, but it was just an estimate, right? It was not used to facilitate your computation in some way.
Well, I guess in some ways it did help us facilitate, because it's harder to you're right, the numerical noise, if it was too low mass, numerical noise would drown out these effects. So we chose a fairly large mass in some ways so that we could see the effect. That's one answer. The second part of the answer is actually these models are fully self-consistent. So it's very hard to match the right mass of Sagittarius at the end. Because the satellite, let's talk dynamics. The satellite comes in, it excites a wake in the dark matter halo, and then the satellite experienced dark matter, a dynamical friction with that wake. So the orbit decays, and that orbit decays depends on the mass of the satellite. But in reality, the mass of the satellite is changing because it's losing mass. So it's really hard to predict exactly how the orbit
final
and how it ends up. So the bottom line is, what I'm trying to say is, because you have, it is just a galaxy with several components and just a satellite, but there's dynamical interactions happening all the time, and we dynamicists love it. So that means it's hard to run a constrained simulation with the right mass, is what I'm saying.
Okay, thank you very much. And I have one more question if nobody else has one, but I don't see any. I see one hand raised. Okay, I think this is going to be a brief one, and then Apostolos Mastiadis will ask his question. So I was wondering if you're going also to use any information about the chemical composition of stars. Is it something that you...
Yes.
Because you mentioned this very nice, that all the stars in our local volume have different origins in the disk. And I was wondering if this can help you, or you can combine it with some information about chemical composition.
I think that is a terrific question. I mean, the other side of that question is also age, because people love to, and chemical composition is an indication of age. And you can imagine, if you look at very youngest stars, we shouldn't see the spiral, right? There is actually a plot in one of Sherman's papers to look at that. So I think chemical composition could be used the same way. There is actually a paper, I'm sure you want to look at this in your free time, but there's a paper led by Adrian Price Whalen, where he's also looking at the ZVZ plane, and he plots contours of the chemical composition. And the interesting thing is that the mid-plane, and he uses those contours, this is really fun dynamics. He uses those contours as indicators of action surfaces. So that's a whole thing. But another thing he found was the mid-plane for stars with different chemical compositions. So the Z equals naught, or the mean Z is different for stars with different chemical compositions. And that's sort of getting at what you're saying. So I think that's a really good idea.
Okay, yes, I will look it up. Thanks.
Yeah, Price Whalen. I'm on the paper too, and David Hogg. It's the same group.
2020 or 2021?
Not sure. Either one of those.
I will look it up. Thanks. So next in line is Apostolos Mastiadis.
Yeah, no, thank you very much for your talk, Kathryn. Maria asked my question about the chemical composition. But okay, I have a lesser one question. It's about the tools you are using. In other words, do you find the code that is adequate to explain the whole situation that you are describing? In other words, say in 10 years' time, will there be any improvements, numerically speaking, that could help you more in this on this issue?
No, love it. I think it's less so, like we are at a point where we can run extremely high resolution simulations. It's not clear to me that it's the n-body codes that are the limitation. It's more that you run an n-body code and it matches everything. What have you learned, right? Do you know what I'm saying? So I'm actually going, there's two opposite ways I'm going. I'm actually going the opposite way. I'm going to simpler things. Using the n-body simulations, yes, but using toy models to actually understand them. And when I say toy models, I mean just well, it wasn't, this paper is not in pulse approximation, but just very simple. We did estimates where we just had stars moving on exactly circular orbits, what would happen with the acceleration going through those plots I showed you. It's almost like way simpler in order to understand than a full N-body simulation, in order to be actually say what really is happening and also interpret the data. You need the combination. So that's one way. The second thing that I'm doing is working more on a sort of statistical analysis that's rooted in dynamics. And I don't have time, that would be an entire other talk itself. But it's based on basis function expansions that are solutions to Poisson's equations. So therefore, it's a way of describing structures non-parametrically. You're probably all familiar with this. But the fact that they're solutions of Poisson's equation gives it a dynamical root. And we're exploring a machinery, just very briefly to give you the words, and then the paper's not out yet, but we're exploring a machinery called multivariate singular spectrum analysis. And this allows us to take series of numbers, in this case, coefficients of the basis function expansion, and correlate them over space and time. And what we're finding is we are able to pull out, so I'm hopeful that we could do something similar to this, to pull out, say, going back to the earlier question that we had from Panos, right? To pull out if we have snails across the disk, are they correlated in some sense with the formation or destruction of a galactic bar, or are they correlated in some sense with a satellite galaxy orbit? And to do this in a statistical way. So I guess I'm going around your question. Like, my focus is not on improving numerical simulations. It's on improving our understanding through highly simplistic arguments, and then improving it by being able to make connections directly from theory through data through dynamically motivated statistical tools, not machine learning.
Yeah.
It's like supervising.
I fully agree with this approach, okay?
Yeah, any other tips? I would be glad to hear them. Yeah, any other thoughts?
No? But this is also, but I think that I'm telling also the students that we have to understand first with toy models first, I mean, the basic ideas, because now computing has become very sophisticated, and as a result, we might lose what is hidden beneath. So I think we have to go a little bit back to.
Yes, we have to stick together. Us dynamicists have to stick together with our toy models.
Yep.
Yes.
Thank you.
So I think there was also a question, a hand raised by George Vasilopoulos.
Yeah, hi, can you hear me?
Yes, we can.
Hi, thanks. It was very interesting for me that remind me lots of stuff that I had forgotten. So I would like to ask, like, for the interactions about the Sagittarius, do we know currently if there are any other dwarf galaxies that have been interacting with our galaxy in the last, let's say, similar time scales as the Sagittarius, or is it?
Yeah, no, so Gaia has, there's been groups who have produced some spectacular results there. So in particular, the Cambridge group, Vasily Bolokarov and all his collaborators, and then the Groningen group, Amina Helmi and all her collaborators. And I need to mention them because they've done a lot for Gaia, especially Amina. But they have uncovered and I think, argue quite convincingly, something of a timeline of history of fairly significant interactions in the last 5 to 7 gigayears from things that, so you may have heard the names for these would be, Vasily's group calls the incident the sausage, and another one the sequoia, and then Amina's arguing that it's probably part of a large merger, the Gaia and Celadus merger. Those happened about 5 to 7 gigayears ago, and those we don't see those satellites anymore. We just see the remnants. There's also these, but they're of order similar scales to Sagittarius, maybe even as big as the LMC in comparison to the galaxy. So why were you asking the question though?
I was just thinking if this could also introduce some kind of noise, because you said that the amplitudes on the simulations and the data are not consistent with each other. So
yeah, no, I think that's a good idea. And there's also the tricky thing is though, as we're saying, well, the reason we haven't published 10 papers on snails because we want to, it's because it's difficult. It sounds easy, right? I've made it sound easy, but there's so many interactions going on like that really, I don't think we're going to be able to delve too far back in history. I think what we'll be able to delve into is about the last giga-year. That's just waving my hands. And so I think the ongoing interaction with Sagittarius may be something recent about the bar, possibly something that we haven't anticipated that we don't see. So maybe we'll be able to use it, perhaps as you're suggesting, as a detection technique, but only, I doubt that we can go back 5 giga-years because the wobbling up and down of the disk itself can set off spirals. So that can erase the previous spirals, if you see what I'm saying. So
yeah, I think I understand. And can I ask something else? It's more like what I was when I was looking at your plot, I think on slide 23 or so, where you were showing the many scales on all.
This one?
Yeah, maybe a little below, a little, no, further, yeah, this one. So perhaps I was looking this too much time and I'm starting seeing things, but is there any reason, like why would you expect the face of the snail to change, let's say perpendicular or vertical to the plot? I'm trying to figure out if there is any pattern. So
yeah, no, exactly.
It seems that they're rotating, but on one direction they are changing phase faster than the other. I'm not sure.
Yeah. Yes. So I think you would expect it to be predominantly a function of your galactocentric radius or angular momentum more equivalently, right? Because as you go to higher angular momentum and further out in radius, all the timescales get longer. So the spirals as you go out should be less tightly wound for a single interaction. I think this case it's too complicated to see it in this case, but conceptually. So if from a single interaction with the same particles interacting, not the same disk interacting at the same time with that interaction, over time, you would expect the least wound spirals to be on the outskirts. Is that making sense just because of the time scale? Are you asking a different question?
Yeah, I think that makes sense what you said, that it should be an angular kind of dependence. Yeah, okay. I think I cannot formulate it very well. Maybe I have some more questions about that, but maybe more it has to do with me being ignorant on many stuff.
No, I think, you know what I think it is it's thinking in many dimensions at once. It's like, and it's tremendous fun, but it makes your brain hurt. And the only reason that I'm still doing this is because I think there's immense potential.
Yeah, sounds fun.
Yes. So
thank you.
I think that we are like out of time, but so I would like to thank very much Kathryn for being here and for giving this very, very exciting talk and showing us these very mesmerizing plots. And I would like to request from everybody, if you would like, before we leave, just to switch on our cameras so that we can have our first group photo, because this is like the first talk of this semester and we haven't taken any photo.
Would you like me to stay on?
Yes, of course. I mean, you are our speaker.
Yes.
It's nice to see you all. Right, and just let me, while you're setting up, thanks for the invitation. It was really fun to connect all the way across to Greece. I hope you're all well over there.
Yes, so just let me wait a couple of minutes more. We lost some people along the way, but that's good for now.
People were shy.
Yes. Okay, I'm going to just take a couple of photos. Okay, I took one. Thank you very much. You can switch off your cameras now. And thank you, Kathryn, again for being here.
Lovely to be here. Thank you for listening and enjoy the rest of the evening.
Thank you very much. Bye-bye.
Bye.
Thank you.
Bye.